And hello, welcome everyone to our Turbulence modeling video series. In the last video, we were talking about the Kolmogorov scale, and we saw also the scales near the wall, which are based on friction velocity. Because like dimensionless wall units, they are based on friction velocity, and that is the characteristic that will help us get the characteristic length scale to get our wall units, and that is very important for non-standard fluid mechanics flows, whether it's flow in a pipe, flow over a wing, and forced convection flows. Now that's part one, so to speak, right? Because they are actually in heat transfer. Okay, so we depart from standard fluid mechanics and forced convection. Standard fluid mechanics, we also have heat transfer. So whatever we just talked about for Kolmogorov scales, they do tend to work pretty decently for heat transfer, okay, in terms of forced convection. Though in natural convection, there is something else that we should know. Okay, because the scales that we are talking about, the smaller scales actually tend to differ for natural convection. And to kind of know this, you need to have some basic knowledge of natural convection. You need to know what the dimensionless numbers are, Rayleigh number, Prandtl number, Grashof number. All these are very important. And of course, you should know a bit about the Richardson number if you're talking about mixed convection as well. And today, this paper I'm referring to for most of this video is called Resolving Fine Scale Structure in Turbulent Rayleigh-Bénard Convection. What is Rayleigh-Bénard convection? I don't know whether I'm pronouncing it right, but anyway, there's convection like this. You see, basically you have a hot plate at the bottom, a cold plate on top, and what happens to the fluid? The fluid near the hot plate gets heated up and it rises to the top, and then it goes to the cold plate and it cools down and then it sinks. So this is Rayleigh-Bénard convection. It's very similar to what happens in our atmosphere, where the air on top, the air towards outer space is cooler, and air closer to the ground, it's hotter. So you have this kind of convective flows, or even in a boiling pot of water, it is a very similar idea as well. So what are the smaller scales in natural convection such as this? So, well, we recall for force flows, the smaller scale is called the Kolmogorov scale. Okay, the Kolmogorov scale, and the assumption is that, hey, remember what we did for Kolmogorov scales? Okay, I just want to leave it out later. Kolmogorov scales, right? Kolmogorov scales. What's the scale that we're talking about here, and how did we get the scales about? Remember, we did it through energy balance. So we had characteristic kinetic energy input determined by this U cube over L, and then it cascades into these eddies, and the eddies will be broken up and it'll get smaller and smaller till at the smaller scale, the main means of dissipation is with viscosity, because at the smallest eddies, the eddies don't break up into smaller eddies anymore. They don't have this so-called turbulent eddy diffusivity, because their Reynolds number is so low that you cannot sustain breaking up into smaller eddies, or your eddies cannot shed. How to say? If you have a big eddy, you can have small eddies like carry momentum away and energy away. But if you have the smallest eddy, there is not enough energy to do this kind of thing anymore. So most of the thing will be from diffusion. And this is what we get when we do our Kolmogorov scales. So we have a nu over L. It will be, okay, eta over L. Eta, it will go as nu cube over epsilon, and you take it to 1 over 4th power. This is the Kolmogorov scale. Now, in natural convection, is this mechanism also true? Okay, you have some mean flow, which is fine. You have natural convection where buoyant fluid rises, hot fluid rises, so you have this some velocity here, a mean velocity, which is not due to some external driving force, but rather, I mean, it's not like you have a pump or a fan that's forcing the flow, but this is because of convection. So you have a different kind of driving force here to drive these eddies, but you still have some velocity mean that's creating these eddies if it's fast enough. So as you do this, how are the eddies dissipated at the smaller scales? Well, if you have the smallest eddy here, I mean, you have viscous dissipation, that is one. However, you know what actually drives these eddies, right? What actually drives these eddies? You know that actually, what actually gives energy to these eddies, that is basically heat, right? Heat actually drives natural convection, and therefore heat or temperature difference, right? Temperature differences are the main driving force to these eddies, for these eddies. And one of the ways you can get rid of this energy in the eddies is, one, of course, you have the heat. You have the heat turn into kinetic energy, which is your kinetic energy of the eddies, and then of course you dissipate it out into heat. You dissipate it back into heat. That's your Kolmogorov scale kind of a thing. That's how we derive Kolmogorov scales. But there's a second way where you can dissipate these eddies. Instead of waiting for the heat to turn into the eddy kinetic energy, the kinetic energy of the eddies, you can just dissipate the heat itself, because there is such thing called conduction. Okay, so you have conduction here. Alright, so if you dissipate the heat over here in these eddies via conduction, suddenly there is not enough driving force to keep these eddies alive, and the eddies will die out. So you cannot just assume that what was true for the forced convection, i.e. that the Kolmogorov scales are the smallest, they are the same over here, because now at the smaller scales, okay, at the smaller scales you have a conduction phenomena that actually can drain energy from your smallest eddies. So now the energy balance is kind of different, because now not only do you have viscosity, which takes energy out of the eddies, you also have conduction that takes energy out of the eddies, and that is done through thermal diffusivity. So in the smallest eddies, you have two dissipation mechanisms for natural convection. One is the thermal conduction, which I was discussing. Then you have which is this viscous dissipation. And of course, when you convert this kinetic eddy back into some heat energy, of course the heat energy is at a lower temperature, right? And for this, the heat energy is at a higher temperature. For here, the heat energy is at a lower temperature. I mean, they are all heat energy, but they are at different temperatures here. So remember your second law of thermodynamics, heat always flows from high temperature to low temperature. So there's a conservation of energy here, which is normal, but this heat, which is dissipated via viscous dissipation, cannot be used to drive eddies, because I mean, on average, second law of thermodynamics doesn't allow for that. So statistically speaking, right? Okay, so there's no eddy diffusivity. Okay, this one I want to remind you again. There's no eddy diffusivity or eddy heat flux at the smaller scales, because at the smaller scales, your eddies cannot break up anymore, so to speak. So they are dissipated via viscous dissipation and conduction for this natural convection. So because of this, we have to come up with two scales now. One, of course, is the Kolmogorov scale, where viscous dissipation dominates, and the second is the Batchelor scale, where the what do you call that? The conduction dominates. So this is thermal diffusivity that drains energy out of the eddies, and most of the time we find that especially for large parental number fluids, this Batchelor scale is much smaller than the Kolmogorov scale. So you can see the relationship between the Batchelor scale and the Kolmogorov scale is simply you just scale it by 1 over the square root of parental number. So for large parental number, the Batchelor scale dominates. Alright, so how then do we derive, let's say, a Kolmogorov scale for natural circulation? Well, I'm not going to derive it. I'm just going to say, okay, let's say you have this. I'm just going to tell you the rough process because it's very, very long derivation, so I don't want to do that. But you have this ratio between your Kolmogorov length scale and your macroscopic length scale, which is like the length scale of the system, and it's given by this formula here. So of course you have kinematic viscosity, but what is interesting is that we have this dissipation rate, and the dissipation rate in these eddies, they are described by some derivatives, some strain rates, etc, etc. I'm not going to do that here. I'm just going to quickly skip all of that, and I'll say, okay, the general idea is that we non-dimensionalize this what do you call that, the dissipation rate, which is due to a mixture of, there's a viscous dissipation, and then of course there is the alpha dissipation, the thermal conduction. So I'm just going to skip all of that. I'll just say that's the main physics behind it. Okay, that's the main physics behind it. And we say that, okay, let's say the characteristic length is the length h, which is, for example, the cell height of this Rayleigh-Number cell. Okay, and I'll say that after you non-dimensionalize this, you will get this correlation here with parental number to the 3 over 8th and Rayleigh number to the 3 over 8th. So that is, your Grashof number is packaged inside the Rayleigh number, and then you have this non-dimensionalized diffusion rate. Okay, so dissipation rate. So this epsilon tilde to the 1 over 4, this is actually a dimensionless dissipation rate, and on average this dissipation rate is governed by the Nusselt number, which is the heat transfer, because ultimately the feeding system here, and your dissipation rate, all right, like always, your dissipation rate here, your total dissipation rate, be it by conduction or this viscosity, viscous dissipation, it has to equal this energy input rate. Otherwise it's not a stable system. It will change dynamically. So we are saying this happens after there's some equilibrium, so-called equilibrium. There's an energy in and energy out, and it's the same. So there's no net energy change for this eddy system. Okay, so on average the dissipation rate will have to equal the feed rate, right? The dissipation rate will have to equal the feed rate here, and the feed rate is governed by, okay, well, lo and behold, your Nusselt number, because that's the heat transfer rate. So the maximum energy your eddies can have, or that's being fed to the eddies, will be determined by your heat transfer rate. And of course you have your Rayleigh and parental number at the bottom here. So I'm skipping all of that, I'm just giving you a rough overview. And therefore your Kolmogorov scales, if you just substitute all of these into here, then you will get this correlation here. Very nice, very neat. Okay, so you'll need to know your parental number, your Rayleigh number, and of course the Nusselt number. And for most of the correlations here, remember we need to evaluate. Okay, evaluate dimensionless numbers. Okay, the fluid properties of them, because all these will be determined by some alpha, some thermal diffusivity, momentum diffusivity. So evaluate the dimensionless numbers at T film, which is equals to T surface plus T fluid, which is also called T infinity, then divide by 2. So this is at the T film. So that's your estimate of this. Okay, and what is a Batchelor scale then? You just divide this by the square root of the parental number, and then you will get this this sort of relationship here. So as to which scale is smaller for natural convection, it very much depends on your Prandtl number. So if your Prandtl number is very big, then your Batchelor scales will tend to dominate. Otherwise, your Kolmogorov scales will dominate. So all of these, I mean, using these correlations here, you will definitely need to know what your Nusselt number, your Prandtl number, and the Rayleigh number is in order to know the length scale. Now, just like for Kolmogorov scales, I mean, we found that the Kolmogorov scale and the near wall scales may not necessarily be the same. So how can we reconcile this thing? So actually, we know that since these scales are actually for natural convection, right? These scales are actually for natural convection. Natural convection has to happen at the interface with the wall, because this is where all the natural convection, most of it's happening. You have the steepest temperature gradients here, okay, and so most of these natural convection occurs in the vicinity of the wall anyhow. So for example, let's say you have a hot plate that's going to heat up some air. So most of the natural convection will happen in the boundary layer. So most of these scales are very much relevant to the boundary layer. Whether it's in the free flow, free shear region, or the boundary layer, these will be some of your characteristic scales. Okay. Of course, actually for this case, we'll need to actually pay a little bit more attention, because there is of course a friction velocity there as well. You might need to take that a little bit into account. For this case here, you can see that the friction velocity, which is based on the wall shear stress, that will be minimal because there is no mean flow, so to speak, to stop. So if the mean flow is going this way, the friction velocity should be, or wall shear stress will point the other way. But here there is no mean flow in this the direction parallel to the plates. So since there's none of that, I mean your whole wall, the wall shear stress and everything kind of breaks down, because it just so happens that these things are not as important anymore. So okay, so these I mean in general, these scales are relevant near the wall. It makes the wall function estimates somewhat less necessary, but if you're talking about flat plate flows, we might need to pay a little bit closer attention. So okay, for example, you have a flat plate flow. If you take from Bijan, Nusselt number actually scales with the cube root of the Rayleigh number. So if you want to put the Nusselt number in here, that's one of the ways. But of course, there's no general rule for Nusselt number or for Nusselt number, because when you have different flow correlations, etc., we might not have the Nusselt number correlation scale the same way. And actually for what do you call this, Rayleigh Bénard convection, for Rayleigh Bénard convection, okay, I think I spelled it wrong again. Where is it? Okay, Bénard. Okay, sure. It's a close enough spelling. I'm not going to put an apostrophe here. Okay, the Nusselt number in the turbulent regime is actually equals to Rayleigh number 1/3. So there's no general rule. But they more or less take this kind of form. Okay, so this is from Paris Chemical Engineering Handbook. Okay, so that's okay. Hopefully you know what Paris Chemical Engineering Handbook is. Yeah, I should go and paste it in the link as well. Let's go. Paris. Where is it? There you go. I'll paste it in the link description, but of course, may not be able to find it so easily online, but yeah, that's the reference I want to put. Alright, so now that kind of covers it for the scales, at least for the free shear region of the natural convection. Okay, for free shear region of natural convection, that covers the length scales that we need to so-called worry about, especially for direct numerical simulation. Okay, so general technique, of course, you for LES scales, you just take the smaller scale, then you times 10. That will be roughly what your smallest LES cell size should be. For Reynolds average Navier-Stokes, just take the smaller scale times 100. That should be your rough cell size, or cell width, or cell length, so to speak. So okay, so we cover the smaller scales in the free shear natural convection zone, and we can talk about mixed convection in the next video, along with some other examples. So thanks for watching. I'll see you guys next time. Bye bye.